Okay, so the power of context-free grammars. Okay. So I'll make some claims, and we won't rigorously prove them. So 1. Okay. Context-free grammars can do anything that DFAs can do. Context-free CFG can generate any language that can be solved by DFA. Okay, and to see how, okay, if you give me any DFA, I can construct a context-free grammar that generates all the strings that will be accepted by that DFA. And to see the basic idea here, you can look at example 25.2. I'm not going to spend too much time on these details. We have bigger fish to fry. Okay. The second, claim that I'm going to make, and this is completely without proof, but you can see other texts which prove it, okay, is that essentially the context-free grammars are equivalent in some sense to DFAs with a stack memory. Okay, DFA with stack memory. Actually, it turns out that they're a little more complicated than DFAs with stack memory. Okay, they're equivalent to non-deterministic DFAs with stack memory. Okay, so non-deterministic, well, we haven't studied non-determinism, so let's not get into that. So, but basically in your mind, imagine that a context-free grammar can do even more than, or basically around what DFA with stack memory can do. And we saw that when you give the DFA stack memory, it can solve the problem 0 to the n, 1 to the n. So DFA with stack memory is more powerful, is stronger than just a regular DFA. And so CFGs are stronger than regular DFAs. Okay. In fact, we just saw that CFG can generate 0 to the n, 1 to the n. Okay. And just to illustrate some of that power, let me show you some of the things that we can do with context-free grammars with ease. Okay, so let's consider some languages. L1 is zeros followed by ones, 0 to the n, 1 to the n. Okay, where n is greater or equal to 0. Let's consider L2 is 0 to the n, 1 to the n, 1 to the n, 0 to the n, where n greater or equal to 0. Okay, so let's see if we can construct CFGs for these two languages. So I'm going to now deviate from the start variable being s, and I'm going to label this language as start variable a. So a goes to either epsilon or 0, a, 1. Okay. We already saw this. This is going to generate zeros, this is going to generate ones, and each time when you put a 0, you put a 1, so you'll get an equal number of zeros and ones. And here, you can generate these strings with b going to epsilon 1, b 0. So you might ask, why am I using different start variables for two different languages? Because now I'm going to talk about combining these languages in various ways. Okay, how to combine these languages in various ways. So let's take the first example, union. So, some of the things we like to do with languages. So L1 union, L1 union, L2. So what is this? It's the strings that are in here or here. So if I want to be able to generate the strings in here or here, so here's what I'll do. Just a simple trick. I take my start variable and I can transition it to either an A or a B. Because that's what union means. So it can either become an A or it can become a B. And then what happens to A's? A's can either go to epsilon 0, A, 1. So the A can go and generate its string, okay, however it wants. And B can go and generate its strings however it wants. Okay, so B can transition to epsilon 1, B 0. And you'll see that now this grammar, okay, which starts with S, and then it branches. It can either go and generate an A, which is in L1, or a B, which is in L2. Okay, and so this guy will generate something in there, this guy will generate something in there. Generating the union of languages that have context-free grammars is trivial. Okay. You just take your start variable and go to the O of the start variables of your original languages. So, and this is why I used A here and B here. It's very important that when you do this, all the variables in your languages L1 and L2, they must all be different. Okay. Now here is an example of a context-free grammar with two variables. Okay. But one subset of the variables, so the A, are all coming from L1, and the other subset of the variables for B are all coming from L2. Okay. Let's talk about concatenation. So what about L1 concatenated with L2? Just as easy. Instead of taking your start variable and going to AB, okay, I take my start variable and go to A, this is A or B, I go to AB. So I replace my start variable with an A followed by a B. And my A transitions in its own way independently. So now you take this A and independently derive it to whatever it goes to, epsilon A1. And you take this B and independently derive it to epsilon or 0A1, epsilon or 1B0. Okay. So let's do some examples for here. So we can take S and go to A, okay, and then go to 0A1, and then replace this A with epsilon. That gives me 0, 1. Let's take my S and go to B, and then once I get to B, I can take my B and make it 1B0. Okay, I can take this B and make it 1B0, so I get 1, 1B0, 0. Okay, now I can take this B and make it epsilon. Okay, so that goes to 1, 1, 0, 0. So you see this is 0, 1 in language 1. This is 1, 1, 0, 0 in language 2. So this guy generates strings that are either in here or in here, depending on which branch you take for S. This guy, on the other hand, let's do an example. So S goes to A, B. Okay, then A can go to, let's say, 0A1, and then B. And then this can go to 0A1, and we can take B to 1B0. Okay, and then we can take A to epsilon, 0, 1, 1B0, and we can take B to epsilon, 0, 1, 1, 0. And look, this is the concatenation of two strings where one is in A and one, in L1 and one is in L2. 0, 1 concatenated with 1, 0. So, pop quiz. Give me the context-free grammar for L2 concatenated with L1. Okay. Now, here's a challenge. Let's see if you can get me the context-free grammar for L1 star, the clean star. Okay. So this guy, I'll give you a few seconds. Okay. 1, 2, 3, 4, 5. So what did you say for this guy? Oh, it's basically the same as this grammar. Instead of S going to AB, S goes to BA. That's all. Okay. What about the clean star? Let's see if you can solve the clean star. Can you give me a context-free grammar for the clean star? Give me 1, 2, 3, 4, 5 seconds. Here we have to use a trick. So what we want to do is be able to repeat any number of times strings from L1. Okay. So what we do is use the trick that we already saw a couple of times. So the trick is that you take my start variable S. Okay. It can either be replaced with A or A followed by S. Okay. This has the effect of allowing me to produce A clearly or AS. Okay, but then the S can become A, so that becomes, so this can go to A squared, okay, or this S can go to another AS, so AS, so this is A squared S, and then the S can become either A, so that gives me A cubed, okay, or this S can become another AS, so that gives me A cubed S, and so on, okay. So this trick allows me to generate any number of A's. A string with any number of A's. Okay? And then I just continue each A independently, okay, using the grammar for A. Or 0A1. So let's see this in action. So I'm going to take S, and I'm going to go to AS. I'm going to go to A. I'm going to replace this S with another AS, so AAS, and now I'm going to replace this S with A. So see what happened? I took this S, replaced it with AS. Took this S, replaced it with AS. Took this S, replaced it with A. Okay. Now I'm going to take this A and replace it with 0A1. 0A1. Then I got my AA. I'm going to take this A and replace it with epsilon. So 0, 1. And I've got AA. I'm going to take this A and replace it with 0, 1, 0, A1. And then I have my A. And I'm going to take this A and replace it with epsilon. So I get 0, 1, 0, epsilon 1, and A. And then I'm going to take this A and replace it with 0, A1. 0, 1, 0, 1, 0, A1. I'm going to take that A and replace it with 0, A1. So this goes to 0, 1, 0, 1, 0. So that's 0. Then 0, A1, and 1. Okay. Then I'm going to take this A and replace it with epsilon. So I get 0, 1, 0, 1, 0, 0, 1, 1. So look, this is in L1, this is in L1, and this is in L1. 0, 1, 0, 1, 0 squared, 1 squared. And I've got the concatenation of 3 strings that are in L1. So you see, I can do union, I can do concatenation, I can do clean star. It turns out that that's all I need to be able to do in order to be able to do regular languages, providing that I can do any finite language. So, exercise, pop quiz. Quiz. Give a context-free grammar for the finite language 0, 0, 1, 0, 0, 1. So L is a finite language. It's a context-free grammar for that. Give you 5 seconds. 1, 2, 3, 4, 5. Okay. Well, if you said S goes to 0 or 0, 1 or 0, 0, 1, that's how simple it is. So it's trivial to get a context-free grammar that generates any finite language. And now you can take finite languages, combine them with union, combine them with concatenation, combine them with clean star. You can get all the regular languages. So that's how powerful context-free grammars are. Okay. So let's erase. I'm going to quickly tell you about parse trees. Okay. And then we're going to look at some of the limitations of context-free grammars. So let's do a speed erase. Aye.